All right. So this is going to take us through just chemical reactions. So we're going to get into chemical reactions. Um, it's going to be kind of an extension of what we've learned with chemical bonding, and it's going to kind of take us through now to this whole process of why the bonding process. We're going to call that process when atoms bond the chemical reactions. They react together to form these bonds. All right, and so chemical reactions are a change in which one or more substances are converted into new substances. Baking a cake, baking soda vinegar, iron and oxygen forming rust. This is copper. This is what the Statue of Liberty looked like. All right, and it's oxidizing. This is what our Statue of Liberty looks like now because of it's oxidized. It's reacted with the oxygen in the air, so it's got a greenish bluish color. All right, but before it actually looked more like a penny. All right, so a chemical reaction is really broken up into two parts. It's broken up into the reactants, which this is going to be crazy, so hang with me here. That's the substances that react. Oh, man. I know, I'll give you a minute to soak that in. And with the products, this is where it gets even crazier. The products are the substances that are produced. Man, I'm hitting you guys with all sorts of knowledge. And so typically in a reaction, all right, what I'll always say is like the reactants come before the arrow. All right, so a typical reaction will look like this. All right, we'll say reactants, arrow, products. All right, and what this arrow means is that the reaction has occurred. Something new is being produced. So that arrow means produces. All right, what does it produce? It produces products. All right, so the left or the butt of the arrow, the left of the arrow is the reactants, the right of the arrow is the products. All right, another way to look at it would be like this, where it's A plus B equals C plus D. You have new products are being formed, even though it's that we'll talk about the atoms are the same, but it's a new product is being formed. All right, so the reactants are over here, the products are over here. All right, and a chemical equation is a way to describe a chemical reaction using chemical formulas and other symbols. So we talked about how to write a chemical formula, various ionic and covalent formulas. We've already talked about that a little bit. So within an equation, these are the things that basically what things mean. All right, so it says produces. When you see an arrow, that means something is producing or being formed. A plus sign, this is, guys, I'm telling you, this is a crazy unit. A plus sign means plus. All right, so it means it's adding to. All right, it's in addition to. S is when you see something in parentheses, it's just telling you the state of matter it's in. The only one that's a little bit goofy is aqueous. All right, and aqueous just means it's a solid, but it's dissolved in water. So when you see something that says AQ, you're like, what the heck? I know it's solid, liquid, gas. That makes sense. Aqueous, that just means it's there. It's just it has been dissolved in water. All right, so you'll have water present as well, but it'll be dissolved in water. All right, Antoine Lavoisier, this guy right here, the father of modern chemistry. All right, what he did with chemical reactions, and this is going to be something that we use in our lab, probably, well, depending when you watch this, probably tomorrow. He established that when he reacted mercury and oxygen, he realized that he had the same amount as what he started with as what he ended with. All right, and so the products that he had matched up, even though gases were being released, etc. The gases that he had beforehand, when it react, I actually think he broke down mercury oxide, and so the gas that was produced, everything that was produced equaled what he had ahead of time. And so he was able to figure out that the mass of the products is equal to the mass of the reactants. All right, and not only is the mass the same, but the total number of atoms are the same as well. All right, so both sides of the equation have to be equal. All right, and this is going to be helpful for us because we're going to do a lab where we have to figure out how much gas is released. Well, if you know how much the reactants were, what the mass of the reactants were, you can get the mass of the products and then just subtract the two, and then that remaining balance will be how much gas was released during a reaction. All right, so you can understand how much is released because this is not magic. All right, we're not making things magically appear or disappear. All right, basically that's what Lavoisier said. It's like it's science. So we're just changing the way things look a little bit, but we still have the same atoms, same number of atoms. We still have the same mass. It's not abracadabra, poof, it's gone. It's just converted from one form to another. It's just changed. All right. And so essentially both sides are the same. All right. So you have the mass of and the number of atoms. So if we had if I said gave you a problem like this, if we have 40 grams of magnesium reacted with 10 grams of oxygen, it produced magnesium oxide. How many grams would be produced? Just add them. It's like a math equation. 40 plus 10 equals 50. All right, and then I could ask you a question like this where I say lithium. How many grams of lithium reacted with 5 grams of oxygen to produce 24 grams of lithium oxide? All right, it's just like a math problem. So if you get 24 and you have 5 on this side, well, to get this, you just do the same thing you do in math. You just isolate the variable. You subtract 5 from each side. It's a new tool, by the way. I'm kind of excited about it. All right, so that'd get you to 19 grams. Ooh, that's a rough-looking 9. All right. I don't know how to change. There we go. This is new. I'm doing this as we go. There we go, clear screen. All right, so it's very similar to math. All right, if you think of what is 2 plus 2, well, it's the same as 4, right? So this side of the equation, 2 plus 2 is 4. 4 is 2 plus 2, so it's the same thing. All right, but instead of an equal sign, there's an arrow. But otherwise, the premise is the same. What you have on one side of the equation is the exact same as what you have on the other side of the equation. So it's the same thing here. If I have x in math, if I have x plus 5 equals 30, well, both sides are already 30. We know that. We just have to know what x is. All right, well, if this side's 30, this side has 5 here already, well, that means x is 25. All right, so both sides in a math equation are equal to each other. It's the same thing with a chemical reaction. Both sides of the reaction are the same, but instead of an equal sign, it's an arrow. All right, so an example of this would be like if you count atoms. So if sodium reacted with chlorine, you have Na plus Cl2 equals NaCl. All right, if you remember how to count atoms, you write out each capital letter. Na is 1, Cl is 2. Na is 1, Cl is 1. These are not equal. This equation is wrong. All right, so what we do to balance a chemical equation, we're going to get a ton of practice at this. What we do is we use something called unit managers. They're called coefficients. All right, so if in this problem, previous problem, we do not have our chlorines do not add up. Remember, we want these to be like a mirror of each other. If I got 2 on this side, I want to have 2 on this side. They should reflect each other accurately. My sodiums are good, but my chlorines are wrong. So what we do to balance it, to write a balanced equation, is we put a coefficient in front. Now, by putting a 2 in front, what you have is a that basically it stands for, I'll just read what a coefficient is. The number placed in front of an element or compound that shows the number of atoms or molecules involved in the chemical reaction. Sometimes referred to as a unit manager. So there's 2 units of NaCl. So there's 2 units of this. All right. So that'd be like saying there's 2 Na and 2 Cl. So when I put a 2 in front, that 2 tells me that there's now 2 sodium and now 2 chlorine. You might be like, well, yeah, but I only have 1 sodium over here. That's right. And so what we'll work on is that you'll have to then put a coefficient of 2 over here to make sure that the equation is balanced. So we're going to add these coefficients. All right, so when you see these coefficients, these just are there to show the number of atoms or molecules that are involved in the reaction in order for the reaction to occur. All right, and this is a correct way to write a balanced equation. All right, so when you look at all this stuff, like this is the chemical reaction that is shown here in this GIF. All right, you look at all this and it's like, wow, whew, that is complicated. What does that even mean? All right, well, we've talked about it. We know what this is. All right, so we've got an element that's in that parentheses S. That means it's a solid. All right, we know that 4, that's a coefficient. That's how many units there are. All right, we don't have to know what all these are. These are different compounds that we're not going to necessarily get into. But we have the arrow means produces. We've got a new compound forming. All right. We have an aqueous. This has been dissolved in water. It's copper 2 nitrate. Here we have gas that is being produced. We got more coefficients. We got water in a liquid form that's produced. 2 units of water are produced. All right, so when you look at something that's pretty complicated, once again, all we're doing is just breaking this down into the simple parts of a reaction. How many units there are. This is the reactants in the equation. This is the 2 things that were combined together. And then this side is the products. All right, that is what is being produced. And that's what we're going to really study. All right, and so we could also do it the other way where I give you a word problem. And I say, all right, I want you to write this. So 2 units of, I don't know how to get my pen. There we go. So if I have 2 units of hydrogen gas, 2H2 combine with, in addition to oxygen gas, O2, it is going to produce 2 units of liquid water. Whoops, I forgot my gases. It tells me it's a gas, so I got to put a G. If it tells you, put it. If it doesn't, don't worry about it. H2O is water, and it's in a liquid form. I'm going to write it like that, just so you can tell it's an L. It's in a liquid form. All right, so once again, I have 2 units of H2, which combine with O2 to produce, so I draw my arrow, it produces 2 units of liquid water, H2O, that's in a liquid form. All right, so these are the type of problems. This is just the basics of a chemical reaction that I want us to investigate.